This video will discuss the pH, one of the most important factors in water and wastewater systems, and also the pKa convention that is useful in particularly discussing the carbonate and phosphate systems. Water, I'm sure you know, dissociates into hydrogen and hydroxyl ions, and there's an equilibrium relationship as described by Kw, where the product of the hydrogen ions and the hydroxyl ions are equal to 10 to the minus fourth. So when those two are equal, the concentration of the hydrogen ions is 10 to the minus seventh. So the convention with the symbol of P is that you take the concentration negative log base 10 of the concentration. So when water is in a neutral condition, sure we all know that that represents a pH of 7. Of course, hydrogen ion is also written as a H3O+. So this figure illustrates the titration of water, pure water, with either a strong acid or a strong base. And you can see that takes only a small volume of caustic or acid in the neutral range to make an extremely large pH change from in the neighborhood of 2 to nearly 12. And that's why it's very difficult to control a pH with strong acids and strong bases for most aqueous systems. Acetic acid is of interest in some environmental matters, particularly related to anaerobic digesters. But as an example here, it's a weak acid, and it's a monoproton, a single proton acid. So acetic acid dissociates into acetate and the hydrogen ion. And the equilibrium relationship you can see here, the Ka value, is the product of the hydrogen ion concentration and the acetate concentration divided by the acetic acid concentration. And that equilibrium is 1.8 times 10 to the minus 5, so the pKa value is 4.7. So here you see the titration curve of acetic acid with a very strong base. And you can see that the equivalent point is where half of the acid is titrated, and that gives you the pKa value of 4.7. The carbonate system is very important in environmental systems. First of all, carbon dioxide exists as a gas at relatively low concentration in most atmospheres. And it's readily soluble in water. And there's an equilibrium for that. We won't get into that discussion today. So carbonic acid is CO2 dissolved in water. So it dissociates one hydrogen ion, and the pKa for that reaction is 6.3. And that is when half of the species are, or that is when the carbonate, the bicarbonate and the carbonic acid concentrations are equal. The next equilibrium is when the bicarbonate decomposes into carbonate ions and hydrogen ions, and the pKa value for that is 10.3. So here's the titration curve of these. The phosphate system is similar, except it has 3 protons. So the first proton comes off of phosphoric acid at a pKa value of 2.1. The second proton comes off at a pK value of 7.2, and the third proton comes off at pK value of about 12.7. So in this chart, you can see that the phosphoric acid concentration is falling, and the other species are rising as the pH increases. And then here we have the buffer point of 7.2. And finally, the increase of the PO4 phosphate radical. And here's the same reactions we've just described. And a number of interesting websites to provide additional information.